Thank you, Mikey. Thank you all. All right, so I will be talking a bit about the internals of CPython. How many of you know what CPython is? Some of you, not all. So for this talk, I'm doing a Jupyter Notebook. Who of you has not seen Jupyter Notebook yet? All right, so it works like this. You write some code, or in this case, I already have it there because I don't type fast enough. And then it runs your code and shows you the output. For example, let's say, whoa, okay, never change your slides at the last moment. For example, this is my Python version. You can see it's 3.7, which is due out later this month. But since we're learning something new, let's be on the leading edge. Right, so I'll be using Python 3.7. Everything you learn here most of it should work in 3.6 as well. It will not work with stuff like PyPy or Jython or MicroPython, all the other Python implementations, because this is strictly about the interpreters of how CPython works. CPython is the implementation of the language, the program that runs your program, which you normally use. Right, so we'll be using these modules, and let's say you write some Python code, you have a .py file. What needs to happen before that file gets run, before the computer does what you tell it to do? So the first thing the computer needs to do is to open the file, get the text out of it, and then the second step is called lexical analysis or tokenization. By the way, can you see that? No, you can't. All right, so let me play around with my browser, bring it up. Can you see that? Who cannot see it? Okay, you two people move somewhere. All right, lexical analysis. This takes a block of text and splits it into words or into units that make sense to the language. You can import the tokenize module that does all this. I have an example module called module.py, which looks like this. It's a very simple Python program. It doesn't do anything really important. This exclamation cat means print me the contents of the file. So here's my file, and then I run the tokenize module on it, and I get a list of tokens. The pieces of the program. So you can see it starts with a name, then there's an equal sign, then there's 3, then there's a new line, another name. It's like the words of this language called Python, right? A equals 3. It strips out all the spaces that are not needed. It gives me just what's important. If you ever took a compilers class in school, if you ever worked with other programming languages, this tends to be the same in any language. The one thing that's different about Python is we have these indent and dedent as tokens. So these correspond to the places in the file where you start an indented block and end it. So in other languages, you would have curly braces or begin and end. Python has special tokens right in the tokenizer for indenting and dedenting. So from this point, the tokenizing is pretty much the same in any language. What happens after that is also similar to what you would have in a compilers class. You can also do this with Python code. If you open the file, pass it through tokenize, you get a list of all the tokens. They have some information attached to them, like where they are in the file, so you can get errors and tracebacks later with the line number information. This is tokenization. You get a stream of tokens of the words of the language. And then Python moves to the next step, which is parsing. This is a bit more complicated how it works internally, but it takes the stream of tokens and constructs what's called an abstract syntax tree, which is a representation of the program that has all the relationships between the commands, the parts of the commands, the expressions, all in a way that makes sense to the computer. It's a tree, so you have a node of the program on top, and then it branches into all the commands you have in the program, and those can branch into expressions and so on. Let's see it in action. I will again show you the module itself. We can open it and we can parse it with the AST module. This gives us some kind of tree object, a module object. This is the root of the tree, represents the whole module. It doesn't give us much information. It doesn't give us information about what it contains. It contains a body, the program itself, and a docstring. Everything in Python has a docstring. In this case, I'm lazy, so it's none. But if I look into the body, we can see there are several commands in there. There's assignment, expression, function definition. If I look back, sorry, this needs to be a small piece of text because of the screen. There it is, assignment, a function call is an expression, and then there's a definition of a function. And if you expand each of these nodes, it will give you the pieces of that command. It'll give you all the information present in the program. You can use the function ast.dump to give you all that information, but it doesn't really look very nice. Or you can write a function that prints it all pretty, but the code of that doesn't look very nice. So let's just run that. So the module has a body. Inside there's an assignment, which has a target, the a variable, and the value is the number 3. So this is 3 gets assigned to a. So this is a tree structure, contains all the information, and theoretically you could just run this. If you get to an assign statement, you assign a variable, and so on. Right? If you want to get into details, there's a file in the Python documentation called full grammar specification, which tells the compiler how to get into this representation. So Python, in the interest of speed, CPython doesn't run this directly. Well, speed and memory. This is a pretty big data structure, so it compiles that into what's called a bytecode, which is yet another representation of what your program should be doing. So let's look into that a little bit. I have some more imports here. We have the same module, 2 assignments, a print, and a function definition. It's in a file called module.py. Let's open that file, get the tree, we did that before, and now we can use the compile function. Who here has used the compile function before? Not too many. So this is actually a built-in function, like you would have int or max or sum. This is built right into the language. You can use it right away. Don't need to import anything, because it's very important, but not that many people use it. So you pass this some text, and it will compile that text into a Python code object. Let's do that. We have some kind of code object. This doesn't really tell me anything. It has information about where it was compiled from. It has all the information in there so that you can execute it. This is another built-in function, exec. Who here has used exec? A lot more. In Python 2 is actually a statement. In Python 3 it's a function, so you pass it a code object, or you can even pass it a string, and it runs it as a Python program. So let's do that. It prints out hello 3 times. Should it do that? Print a times b 3 times hello. That should be good. Right? So that code object has all the information needed to run the program. we can use a code info function to tell us what is in the code object in a pretty way, because that is a file name, it has lots of argument counts, a stack size, it has a list of constants, so anything that you assign somewhere, like if you put a number in the program file, that gets assigned to a list of constants, or a tuple of constants, which the program then can reach into and use the values. So here we have the 3, the hello, there's a 1 somehow, there's a code object for the function, we'll get to that later. There's the name of the function, since Python names everything and retains the names, and that needs to be available. There is none, pretty much every program needs the none constant. And there's also some tuple here. It also has the names of variables. Again, Python lets you, Python retains all the information about your program. So all that, even the internal names of the variables, which don't really matter to the running of the program, everything is stored inside. I have a simple function that goes through all the attributes of the code object and prints them out. Let's see what we have. You can see before it was formatted a little better, but here we have pretty much the same information. For argument counts, we have where it was compiled from, what line number it was compiled from, and we have some other stuff like this co_code. And that is actually the program itself, represented in the interest of memory and speed as this indecipherable piece of binary data, which we will analyze now. So if I, let's skip that. So that is what is called a bytecode. Who here has not heard the word bytecode before? Everybody has heard. You've all read my abstract, right? Okay, who knows what bytecode is? Everybody. Okay, well, I'm preaching to the crowd here. So here's our module. We can compile it, and let's look at the bytecode. So it's binary data. You can split it into individual bytes. Works like this. And this is my program pretty much. So how do you decipher that? How do you look for structure? You can see that there's always a big number and a small number, and big number, small number, big number, small number. So the individual instructions encoded here are always in pairs of 2 bytes. There's an instruction, like what the program should do at this point, and there's an argument, the data that this instruction should use. In many cases, the argument is 0 or a very small number. There's a helpful module called dis, short for disassemble. This was added into Python like in the very early stages when they abbreviated everything before they learned that longer names are actually better for remembering stuff. So dis will disassemble, which means turn the bytecode into something you can actually read. Let's do that. And we can see that the 100 is short for load constant number 0. So when the program gets to this instruction, it will reach into the list of constants and take constant number 0, which happens to be the number 3, and load it into its internal stack. Right? So it'll get the number, put it aside to work on later. Next is store name. So this 90 refers to the instruction store name. What this does is it takes a value from the stack, in this case the number 3, and it puts it in a variable. So it assigns the name A to the value 3. Right? So that was line 1 of our example program. Line 2 is similar. It takes constant number 1, which is the string hello, puts it in a stack, and then from the stack it stores it in a variable. You can see that these instructions are very very simple. They don't do a lot. You have to combine a lot of them to get some meaningful operations. They're very minimal, although in recent years, Python has added some more powerful ones. Usually they're like, put something from somewhere and put it somewhere else. Or get two values and do one single operation with them. This is a function call. It's a bit more involved. So first it loads whatever is in the variable called print. Then it loads whatever is in the variable A and B, and it puts these values on a stack. So you have a stack with print, A and B, so print, 3, and the string hello. Then it does binary multiply, which means it takes two values from the stack, the 3 and the hello, and it multiplies them together. Somehow magic happens and you have hello, 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 and it puts it back on the stack. So now on the stack you will have the function print and the string hello, hello, hello. And then it will call a function with one argument. So it'll get the argument, get the function, call the function on the argument, and print will return a value which is put on the stack automatically, and pop-top removes it from the stack. Who is lost at this point? Some people. Sorry. If you have, I can explain it in more detail later. Now I will go on. So creating a function. So the next line here, next command, is creating a function, which is a very easy operation because you're not calling the function, you're just making it, so that it just defines a function. So basically, this gets some constants, like the name of the function, the code it should run, and this one is a list of the default values. It calls the instruction make function, and it stores it as the variable func, right? So again, making a function is decomposed into the series of small steps. All that is put in binary form into the code object. You can call the this module with -m on some file. It'll print out whatever bytecode that would get compiled into. Right. If you wanted to know what numbers correspond to what instructions, you can use the dis.opmap dictionary, which will give you the numbers or the names of the different operations. I will get to functions later. Right now, let's see how you can get these code objects and put them on disk, because all what happened now, the tokenization, the parsing into the syntax tree, and generating the bytecode, this is a pretty expensive operation. It takes a lot of time. So in the interest of speed, Python caches this. Python will take the result of this and put it on disk, so next time, if nothing changes, it can just read it off the disk. Who here has seen a PYC file before? So that is the Python cache. That is exactly the result of tokenization, parsing, and bytecode generation. Let's look a bit more on how this works. So let me go through the steps again, since this is a new notebook. I have to do this again. So if I look into my PyCache directory, I see that there's a PYC file, which is generated whenever I import a module. If I read it and look into the bytes there, there's this lot of numbers. Can anybody see a pattern in there? Not really, right? So let's dive more into this. So this is serialized data. Serialized means it gets some data structure that's in memory and make it into a binary string. For example, most of you should be familiar with the JSON module. Anybody not familiar with that? Okay, sorry. So what that does is it takes some data structure which exists in Python in memory, turns it into a string. So this is a string you can save to disk or send over the internet. And there's another function that loads the string and turns it back into the Python data that Python can work with. The PYC file is made very similarly, except it's not JSON. It's another kind of serialization format called Marshall. If you ever want to use Marshall for your own stuff, don't do it. It's made specifically for Python bytecodes. But it just takes the code object and it can turn it into a binary piece of binary data, and then it can load it back, and it'll be exactly as before. All right. So let's see. What I did here is turn the code itself into binary string. Let's see what's in the binary string. So this is actually very similar to the data that's in the PYC file. What it is the PYC file has something in the beginning, some header, and then we have the marshaled code object. I can actually see that the first 16 bytes are the header, and that everything else is the same as the code object. So what is this header? The first 4 bytes are a return new line. This is actually a magic number. It's called a magic number. You can import magic number from importlib.util, and this tells me what version of Python was used to produce this PYC file. So if I loaded this with Python 2.7, it wouldn't work, right? Python would look at the magic number and see, this is some other Python, or maybe it's a text file, or maybe it's a PNG image. I don't really want to run this as code, right? So the magic number, the 65 is the actual version of Python, and then it has 3 numbers that make it a little less likely for the object to work if you somehow mangle it. For example, send it through email with some old protocols. This could get mangled and won't work if the file is damaged in any way. The next 4 bytes are all zeros. This is actually new in Python 3.7. They added some flags here. So there are some other kinds of PYC files which would get something other than zeros here. But for most code objects, you will get 4 zeros saying how this PYC file was made. The next 4 bytes are 78, 99, 18, 91. Is that familiar to anyone? Not really. So if I turn it into a number, it's this really huge number. And if I take that as the number of seconds since 2070 from timestamp, it'll tell me when the Python file was last modified. So if I change the original source code, save it again, this timestamp will change, and Python will discard the cache and do the compilation again. Right? So this is one of the ways the cache invalidation works. The other way is the final 4 bytes of the header. This is 74 and all zeros. If I turn that into a number, it's 74. Anybody can take a guess what this is? So this is actually the length of the file, right? So how many bytes are in the file? I can get that with the stat function. It's very fast operation to get the size of a file. So Python doesn't have to read all of the source code to see if the cache is still valid. Right? It uses information that's very easy to compute. Puts that in the header, and if that matches, then it will use the bytecode cache. All right. I'm getting near to the end. Let's look at another piece that you need to actually run your code. So what we had up to now is all immutable data. It's code object. The code object is generated once, and then it doesn't change. Right? You can't change it in any way through Python. What Python then does, it wraps this code object in objects that are mutable. This is actually something I skipped before. I'm sorry for that. So if I import my module and look at the function defined there, that is a function object, an object that represents a function. This is mutable. You can assign custom attributes to it. You can change it. If you have two different function objects, you can modify one. It won't affect the other. Each function has its code object, which tells the function what it does. And I think I'm done here. So whenever you make a function, it wraps the code object with something mutable. Whenever you make a new function, for example, if you make functions in a loop, they will all share the same code object. They will just have different wrappers around them that you can play with, and you can name them in different ways. You can change their doc strings, and so on. So that was a function. Then we get to frames, which are objects that get created when you actually run something. So when I call a function, a frame object is created, and the frame object keeps information about what function I'm executing and where I am in that function. What's the next instruction to run? So let's see. Let's import inspect, which is a very nice module. If you're interested in this, read the docs of inspect. I defined two functions that call each other. There's an inner function that sets some variable, then gets the current frame of execution, and then returns it. I have an outer function that calls the inner one, right? This, hope it's clear to everybody. So what this does, it returns a frame object, and you can see here that it's in a function it's in the inner function, and it's at line 5. Right, so this is the state of execution. So this inspect.currentFrame gets the state of execution of this function as it's being called, and gives me information about the state. This is also a mutable object. You can change this, and Python actually changes this. When I move to the next instruction, it doesn't make a new frame, it just changes the number of the next instruction. So you can see this is on line 5, which is not this line, but this line, because before I printed the frame, Python finished going through the function. So the frame ended up being at the last line, and then Python doesn't use it anymore. The function has returned, but the frame object, I've kept a reference to it so I can see what was there. So what's inside a frame object? It has some code. It has the last instruction that was run. It has the line number, which is actually computed from this instruction. It has some locals. These are the local variables, so the values the function uses. And it has reference to the frame that called this one. Right? So when the function returns, execution goes to the frame that called this one. Right? So when I return frame here, I continue there. So that's how Python knows where to return the value to. In this case, we have a code object. We have last instruction was at the end, line number 5, a dictionary of the locals. It's not actually stored as a dictionary, but Python formats it this way. When you ask for the locals, it will do some magic. And of course, the back frame. You can play with this. You can write a function that gives you the current line of execution. This is what's also used in Traceback. So if there's some error, you can see what called the function. I think I'm out of time, so I'll not go into this. Yeah, sorry. So when a traceback is printed, you can see the line numbers and functions of everything that called that caused the error. So that's made by walking this stack of frames. So you have the current frame, the parent frame that called this one, the parent frame that called that one. All this is generated from the frame objects as the exception bubbles up your code. And I think I'm
okay. We have
timed perfectly. All right.
So
there is some time for questions. I would be very happy to take questions now or later. I think I have one here.
All right. So we have a question from Slido. Guido said, if you want your code to run faster, you should probably just use PyPy. So why not move to PyPy? What is the main advantage of CPython implementation?
The main advantage of CPython is actually that it's simple. I could give a 20-minute talk on how this all works. I think I just did that. Maybe 30, right?
Yeah.
If you know something about this, if you program in C, you can just jump in and understand this. It's gotten a bit harder along the years, but people still do this. It's not something beginners would do, but it's not that hard to read the code, understand what it does once you have a little bit of background in compilers and interpreters. PyPy, on the other hand, is based on cutting-edge research. So you have to read the papers. There are micro-optimizations, so it's not that easy to get into, right? So only a little number of people can actually make changes to PyPy to understand what it does. So yes, it is faster, but also in Python, speed doesn't always matter that much. If you want to optimize a little piece of your code, you can just write it in C, and C is not a very easy language, but for stuff that needs to be fast, it
still has a learning curve that's better than learning how to PyPy.
Well, PyPy implementation is yet on a different level.
All right, another question is, can you recommend a library or framework for rewriting the AST on the fly?
I cannot, sorry. Search Google or just use AST directly. It's very cumbersome to do this. And I've seen some libraries that try to make it easier, but it's really depends on what your use case is for this, what you want to do. So
yeah. All right.
Google yourself.
So we have a beginner question. As a beginner, why would I want to use CPython? For debugging, maybe?
As a beginner, well, you would want to use it because that's the Python you get from python.org. That's the standard reference implementation. And all the other implementations are catching up to it. Like CPython sets the standard of what the Python language is. So we have 3.7 almost ready. And PyPy is, I don't know, 3.6, maybe not yet even. So they're adding the features from CPython to the other implementations. So that's one reason. Also, it's very common. Everybody has knowledge of it. Everybody else uses it. So if you have a question about the internals, you can ask basically anybody. All right,
around. I'm going to actually swap those questions because I think the second question, somebody swapped that question. Great. Some people are confusing CPython and Cython. Maybe you want to clarify this? That's the last question we have time for.
I was talking about CPython. Cython without the P is something completely different. research that.
And CPython is something that doesn't exist.
And I will talk to the website people to put my notebooks up, but that will probably happen after the conference.
Thank you very much, Petr.